For the function f of x equals 5 minus the cube root of x, we want to determine intervals where the function's increasing or decreasing, find the local maximum and minimum values, the intervals for concavity, as well as the location for inflection points. So we basically want to find it all. So I have my list here, increasing, decreasing, local max, and local min. So let me just make a note that these first four items we can find using our first derivative. And then when we move on to concavity and inflection points, we'll find that information using the second derivative. So let's get started. I always like to start with the domain because if there's any domain restrictions, we're going to need to pay attention to those. So our function is 5 minus the cube root of x. And because this is a cube root, it's an odd index, then our domain is going to be all real numbers. We don't have any restrictions inside a cube root function. So let's go ahead and move forward onto our derivative. And before I compute the first derivative, I want to remind you that you could rewrite this function as 5 minus x to the 1/3 power. And that might help you for computing the first derivative. So the derivative of 5 is 0, and then the derivative of negative x to the 1/3 will be negative 1/3 x, and then remember we subtract 1 from the exponent, so that'll give us a new exponent of negative 2/3. Now we want to go ahead and find some critical numbers here because we're interested in looking at whether the first derivative is positive or negative, so we need to figure out where it's going to change sign. So I'm going to go ahead and work with this first derivative and manipulate it a little bit more algebraically first. So we have negative 1/3, but x to the negative 2/3 is really 1 over x to the positive 2/3 power. So our first derivative could be written as negative 1 over 3x to the 2/3 power. So I'm going to go ahead and use this version of my first derivative to find my critical values, my critical numbers. So I'm interested in finding where the first derivative is equal to 0, as well as where the first derivative is undefined. So setting the first derivative equal to 0, negative 1 over 3x to the 2/3 power is equal to 0. If we were going to solve this equation, we would multiply both sides of the equation by what's in the denominator, which is the 3x to the 2/3 power. But if I multiply both sides by 3x to the 2/3 power, 0 times 3x to the 2/3 power is just going to give us 0. So we'd end up with this statement of negative 1 equals 0, which is clearly false. So that tells me that the first derivative never equals 0. We don't get any solutions to that equation. However, if we look at the first derivative and think about where it's undefined, because it is a fraction, that most certainly will happen whenever the denominator is equal to 0. So the first derivative will be undefined when 3x to the 2/3 power is equal to 0, the denominator. So you could think of it as dividing both sides by 3. And then just to review this algebra, because we have x to the 2/3 power, we would raise both sides of the equation to the 3/2 power, the reciprocal, because when we multiply our exponents, remember we're multiplying 2/3 times 3/2, and because those are reciprocals, when we multiply those, you get x to the first power. We just get a 1. So in other words, we get x is equal to 0. So this is our only critical number. And it's also good to note that, remember, it's only a critical number if it's in the domain of the original function, but since our domain was all reals, 0 is in that domain. So now we're going to take a look at the sign of the first derivative around 0. So we're looking at values smaller than 0 and values larger than 0. So we're going to test some numbers. And I always like to do the test down below my number line because I don't want to confuse my test values, my test numbers. I don't want to confuse those with critical numbers. Sometimes I even do them in a different color like I'm demonstrating here. So we're going to test negative 1 and positive 1. but we could test any value smaller than 0 and any value larger than 0. And remember, our testing is going to occur here in our first derivative. So we're going to substitute in a -1. And perhaps it's also worth noting, let me back up a second. And let me remind you that you could actually rewrite your derivative in a different form. If you didn't like -1/3x to the 2/3 power, that could also be rewritten as -1 divided by 3 times the cube root of x squared. If you had chosen to rewrite it as a radical, that would be fine too. These are equivalent. And you might actually like the radical form better for testing if you're trying to do this without a calculator, because if we are going to substitute in -1, but it's going to be squared, we know that that result is going to be positive no matter what. So the denominator is positive, and then we have this negative out in front. So overall, it looks like we're going to end up with a negative value there. And then if we substitute in +1, the same thing occurs. When I substitute in a +1, I'm also going to get a negative value. So remember, these negative signs here, the negatives, this means that the first derivative is negative. That means the slope is negative. So if the slope is negative, that means that the y values are getting smaller. So the original function, the original curve, is decreasing. So this means that the function is always decreasing over its entire domain. So therefore, we can say that it never increases, and it's going to decrease from -infinity to +infinity. It's okay to include 0 in this interval because the domain of the function was all real numbers. 0 is in the domain. Now, we only have a local max value or a local min value if you have a change in sign in the first derivative, which we don't. The first derivative is negative throughout, so that means we don't have any local maxes or mins. So now we're ready to move on to concavity, which means we're going to analyze the second derivative. Now you'll notice I put a box around this version of our first derivative because this is what we used to find critical numbers, but it would actually be more beneficial to back up our work and look at a previous version of the first derivative, because this would be easier for us to use as a jumping off point for finding my second derivative. So I'm going to use the -1/3 x to the -2/3 power as my jumping off point to help me compute my second derivative. So let's go on to f double prime then. So if my first derivative was -1/3 x to the -2/3 power, then my second derivative will have -1/3 times the -2/3 x, and then we're going to subtract 1 again, so that's going to be -5/3 for my exponent on my second derivative. So f double prime should be +2/9 times x to the -5/3 power. And that negative exponent, once again, I'm going to rewrite that as a fraction, so that'll be 2 divided by 9x to the 5/3 power. Or if you're a person that prefers radicals, you could write it as 2 divided by 9 times the cube root of x to the 5th power. Either one of these will work for our second derivative. Now our goal right now is to figure out the concavity of the graph. So we need to find out when is the second derivative positive versus when is the second derivative negative. In other words, we need to look for a change in sign, a possible change in sign in the second derivative. And a function is only going to change sign at either a 0 or a place where the function is undefined. So this is going to look very familiar to what we did earlier when we were finding critical numbers. We need to look for where the second derivative is equal to 0 or where the second derivative is undefined, because those are the only possible places where the second derivative could change sign. So I like the first version here of my second derivative, the 2 divided by 9x to the 5/3 power. So I'm going to go ahead and use that version of the second derivative and set that function equal to 0. And again, if we were to actually show the algebra to solve this equation, you would be multiplying both sides of the equation by 9x to the 5/3 power. But when I multiply 0 times 9x to the 5/3, 0 times that is simply 0. I didn't show that earlier, but I want to make sure you're super clear on the algebra, which gives us the statement of 2 equals 0, which is certainly false. So this is another never. The second derivative will never equal 0. So now, will the second derivative ever be undefined? And the answer to that was absolutely, because we have a fraction, and a fraction will be undefined when the denominator equals 0. So we'll set 9x to the 5/3 equals 0. Divide by 9, so x to the 5/3 power equals 0. And then technically we would raise that to the reciprocal power, which would be to the 3/5 power. But 0 to the 3/5 is going to just be 0. So when x is equal to 0, the second derivative is undefined. So that's a potential place where the second derivative might change sign. So let's go ahead and take a look at the sign of the second derivative by testing. So once again, we'll test a number smaller than 0. How about -1? And a number larger than 0, maybe 1. And we're testing into the second derivative because we're looking to see whether the second derivative is positive or negative. So this time when I substitute in a -1 for x, I have -1 to the 5th power, which will be a negative number. And then the cube root of that will also be a negative number. So I get a negative this time for the second derivative. However, when I plug in +1, that will certainly yield a positive result. So the second derivative is telling us whether or not the graph is concave up or concave down. So this negative second derivative tells me that the graph of f of x is going to be concave down, and then it's going to change to concave up since the second derivative is positive. And therefore, we have a change in concavity here at 0, which is going to tell us that we have an inflection point. We've got a point where the concavity is changing. So now we can finish filling in the information all the way back to the top. So based on our second derivative, our graph is going to be concave up from 0 to 1. And if you're a person that's worried about writing 0, 1 because you might mistake this for a coordinate or a point, then you can be fancy if you want to and say x is an element of that interval. I could have written that up here as well for the decreasing. X is an element of, if you wanted to. So it's concave up on the x interval from 0 to 1, and then it's going to be concave down on the, I'm sorry, not 0, 1, go back. It's not from 0 to 1. Let me go back and show you. Looking at your number line again. There we go. Okay, sorry. Don't want to move too far with that mistake. We said this positive second derivative means that it's concave down. So it's concave down everywhere to the right of 0. So that's the perfect example where I accidentally grabbed my test number of +1 and I shouldn't have. So we are going to be concave up from 0 to infinity. There we go. And then we're concave down when the second derivative is negative, which will be from -infinity to 0. And that means that we have an inflection point at 0, but we want the entire point, which means we need to go ahead and plug 0 back into the original function. So we need to evaluate the function at 0. So that means we're finding f of 0. So back to the original here. Oops, sorry. The original function here, f of x equals 5 minus the cube root of x. So if this is going to be 5 minus the cube root of 0, So that means that the inflection point is going to be the coordinate 0, 5. 0, 5 will be my inflection point.